live. I'm Katleho and this is Tracy.
Hello, Katleho. That was good. Wow.
Yeah,
We're
what?
so excited. My goodness. Well, we're here.
How are you?
Fine, and you?
Good, thank you.
It's Tuesday already. Can you believe it?
It is. I can't believe it.
I know.
When did Monday go? When was Monday?
I don't know. I lose track these days.
I know.
Yeah.
Anyway, what are we doing today?
Today, we're going to do graphs and equations of motion.
Okay.
So last week, Phil very nicely did some graphs and did instantaneous velocity and average and all sorts of things. So we're going to do a little bit more graphs
Okay.
today, and then we're going to jump into the thing the great teens really love.
I know.
Or not.
I know.
Equations of motion. So it's actually a really nice section. It's
Okay.
lots of calculations, no experiments, unfortunately, but
Oh, okay, but that's okay.
it's all calculation based, but it's really
So they're
cool
going to be
stuff.
taking notes.
Yes, and they're going to get the calculators out, and they're going to make sure they know what we're doing.
Okay,
Yeah.
cool.
Cool.
You can go prepare that, all
thank
that,
you.
while
Okay.
I let you guys know about our prizes. Because it's Tuesday, guys, you know that we have plenty of prizes. We have our Casio labeler, and we have our Casio calculator. And by now, you know, grade 10s, that this goes out to the most excitable mindsetter on the page. Facebook.com/LearnExtra, and our Twitter handle is @LearnExtra. Guys, you can ask anything that you need to ask. This is good because I know that some of you have done this in class, so this is nice to revise it. And if it's the first time you see it, get that paper and pen out and start jotting down notes because you are going to be ahead of the rest. Thank you to Liberty for bringing us such an awesome show. Over to you, Tracy.
Oh, thanks, Kakleho. Okay, brilliant. Guys, get going on the Facebook page. I have one of those labeler thingies, and it's my favorite toy. Anyway, moving on. So, we are looking at graphs and equations of motion. Now, I know last week you did a little bit of this, and I'm hoping some of you have done this in class. If not, because you're a little bit behind, please don't stress about it. Stick with us. It's always good to have it done in more than one way. It's always good to relook at things. But when we look at graphs of motion, there's a couple of things we need to remember. Okay, first of all, time is always shown along the x-axis, the horizontal axis. That's really, really important. Time is what we call our independent variable. So when it comes to equations and graphs and that sort of thing, time is the thing we actually have the most control over. So something like, I'm hoping you saw this last week anyway, when you look at a ticker timer and you use a ticker timer tape to create your graphs or to look at the equations, the time is the thing you have the most control over. So that's why it becomes your independent variable. Okay, it's the thing you control. On your y-axis, that's your dependent variable. That's the thing you end up measuring. We're going to put displacement, velocity, and acceleration. Okay? Sometimes displacement is referred to as change in position. There's a little bit of a textbooks and stuff are changing what we call that. So whether your teacher's calling it displacement or changing in position, it doesn't really matter. Change in position is just very broad. Okay, displacement is the correct vector term for it. And that, of course, doesn't matter whether it's horizontal, vertical motion, doesn't make a difference. Number 2, you must use a suitable axis. Now, that depends, a suitable scale. Now, you need to think very carefully about what the question is giving you. Sometimes you are required to draw an accurate graph. That means you're going to have a whole bunch of points that you're going to need to plot. Then the scale becomes very, very important. If you're looking at a sketch graph, the scale's not so important anymore, but you still need to have values, okay? Then, both axes have 0 as the origin. Grade 10s, particularly for those of you who do life science. I know that in some of your subjects, you're able to do what we call cut the graph. So you cut the axis because you know that your first reading or the first thing you're going to plot on the graph is quite far down the axis, so you don't want to leave this whole big space of empty graph. You don't ever cut your axis in science. Okay, you must start, you must have an origin, 0, 0 from both scales, horizontal and vertical, okay, and then you choose a suitable scale, depending on what you have. They don't have to be the same on both axes, because it depends on what you've measured, how far it's gone, what time sort of scales you're using, but you cannot cut your axis. That's very, very, very important, grade 10s. And then, this one, oh, I beg you, grade 10s, you can never go back in time. In other words, you cannot have a negative time value in any instance. This is really important with graphs because we're going to look at things where we look at the calculation of gradient, and that becomes a problem because in maths it doesn't actually matter which way around you calculate your gradient, and it doesn't matter what you choose as your positive and as your first and your second points, but it does in science because you cannot get a negative value for time. You cannot go back in time as much as we wish we could. Okay, so let's go on to what our graphs will look like. Now, what I'm going to do is this is more a summary of the graphs we can end up drawing and what their shapes are going to be. Grade 10s, your shapes are going to be always the same. Whether it's a graph with lots of different points and pieces and bits and pieces on it, or whether it's just one motion, so it's one thing that's moved, the graphs can only do certain things. Why do your graphs always look the same? Because we only deal with linear motion at school level. Linear motion means we only deal with motion in one plane, and also means that we don't go and decide, for example, that we're going to give you a non-constant acceleration for an entire motion. Okay? If the acceleration changes, we have to start again, and we split up our motion into separate sections with constant acceleration. So we have linear motion, which means we get really nice graphs. Okay? So when we think about what our displacement time graph would look like, we have x, delta x, okay, this would actually need to be called delta x and delta t because we're looking at the change in time and the change in displacement, and that would be in meters, that would be in seconds. Even though we're looking at a sketch graph, we're going to keep the SI units, which is meters and seconds. If you're given a question where they have looked at motion over hours and kilometers, then you can change those kilometers an hour. That doesn't make a difference, but the SI unit is meters and seconds, okay? So if we have constant velocity, that means that we are constantly changing, okay? We're going at the same rate, which means every second we're changing our displacement by the same amount. And the first thing we're going to look at is constant positive velocity. That also means that we're looking at a displacement that goes in our positive direction. And that also tells us that we're going to end up with, and this is really nice, a straight line. Now that straight line, I've drawn it almost from the origin. It doesn't have to be from the origin. Okay, it will have a gradient. It could be from this part of the graph, okay, if we didn't start at the 0 point of displacement. So when we look at our reference, remember we've got a frame of reference. If my frame of reference is here, is where I'm standing, for example, but my motion starts where Katlego is sitting, then my displacement cannot start at 0 because I didn't start at my reference point, okay? Doesn't really matter. The point is it gives us a nice straight line, okay? That's for positive velocity. What happens if we have a negative velocity? A negative velocity means that it's going in the opposite direction, and we can also and what that means is then my graph will change direction, okay? Displacement can be both positive and negative. So if I actually extend my graph over here and I go, well, what happens if I started my 0 point, but I've now decided that going away from me in front of me is positive, but going away from me behind me is negative, and somebody now is traveling behind me, okay, is going away from me towards the board in the negative direction, and that means my displacement is actually getting more and more and more and more in the negative direction, okay? Displacement's a vector, positive and negative direction. So of course you can have a negative graph. What do I need you to get from this? Straight line, constant velocity. What happens if we have constant acceleration? Now, acceleration means that your velocity is changing. So it's a case of you can either have positive acceleration or you can have negative acceleration. Generally speaking, grade 10s, when we talk about negative acceleration, we talk about the fact that it's slowing down, like when a car brakes to stop at a stop street or a robot. What's important here is with acceleration, your velocity is changing. And depending on whether it's getting faster or slower, it depends on how it changes. So if we have a positive acceleration, that means every second it's getting faster and faster and faster. So every second, the object covers a greater distance in a shorter period of time. And your graph becomes a curve. Okay? Your graph becomes a curve. And that curve's the wrong way around. Your graph becomes a curve. Okay. Shorter time period, bigger distance. Okay? Shorter time period, bigger distance. This is positive acceleration. Okay? So this is where it's going to get faster. When it's slowing down, let's consider it as a negative acceleration, then what happens is my graph does not do that. It doesn't do all squiggly thingies. It starts to slow down and curves the other way. So what happens here is less distance, that's my height, over time. Okay, so it's slowing down. It's getting slower and slower and slower. Last thing we can look at is what happens if the car's stationary. This graph will be a straight line again, okay, but it can be in several points because it all depends on where the object is. So we could have a stationary vehicle at a certain distance from my stationary point. It could be actually at 0, so on my axes. It can also be negative. Okay, now if I extend my line, so let's just make my graph go into the negative. Of course it can. It can also be there. But it's a straight horizontal line. That tells me that no matter how much the time goes past here, the displacement from my original position hasn't changed. It is stationary. That also means it's got constant velocity. It's a straight line, which is great. It just happens to have a constant velocity of 0. Okay? So, that brings us to our velocity time graphs. Velocity time graphs are really, really important. They're actually very, very, very useful to us, grade 10s, okay? Velocity time graphs can give us a whole bunch of information, and in fact, they're far more useful to us than displacement time graphs or acceleration time graphs. Because from a velocity time graph, we can find both the displacement and the acceleration of our object. Brilliant. Constant velocity, now this depends on the direction in which the object's moving, can either be positive or it can be negative. Okay? Positive or negative. Constant velocity, no change in velocity over time, which means it stays at the same rate. Positive just means it's going in the positive direction. Negative is going in the negative direction, whatever that might be. And it's a straight line horizontal to the time axis. Okay? No change in acceleration. What happens if we have constant acceleration? Now, this, like we said with displacement, can either be positive acceleration or it's going to be negative acceleration. If it's positive acceleration, we are going to assume that means that it's speeding up, it's getting faster. Constant, we have an acceleration that is the same rate, which means that our velocity is increasing by the same amount every second. It becomes a straight line, okay? And it can start from rest, so that means my original is 0. Might not start from rest, which means it can start from there and goes up. All depends on where we're starting as our 0 or reference point. We can have a negative acceleration, which means it's slowing down, okay, which often will tell us that we start from some velocity and it now gets slower. As time goes down, this can go well beyond the negative point. It all depends on the situation. Generally, we'll go beyond into the negative velocities when we're looking at vertical motion, but we're not going to worry too much about that this year. Doesn't have to go end at 0, does not have to end there. It all depends on what section of motion we are looking at, okay? If it's stationary, well, if it's stationary, there's only one place that this graph can go, and that is on the origin. If it's stationary, velocity is 0, not moving, okay? So that actually makes it quite simple. So I'm hoping what you've also realized here, grade 10s, is that not one of these were curved. Displacement time graph, we could most definitely get a curve off. Velocity time graph, because we only deal with linear motion, so we only deal with constant acceleration, we don't get curves in our velocity time graphs. They must be straight lines. They're either going to be horizontal straight lines or they're going to be at a slope. That leads us to our last type of graph that we can get, which is acceleration time graphs. Okay? Acceleration time graphs are probably the nicest ones we have because actually they can only look into three ways basically. If we have constant velocity, that means the velocity isn't changing. If our velocity isn't changing, there is no acceleration. No acceleration means zero acceleration. My graph goes on the x-axis. Simple, straight line, nothing difficult. Now, this graph, by the way, the constant velocity one over here where a is 0, that could be for an object that is moving at constant velocity or an object that's stationary. Because an object that's stationary has a constant velocity of 0. Okay, doesn't make a difference. If we have a constant acceleration, I've said this to you already. Acceleration can either be positive or it can be negative. One of the two. If it's positive, we will only ever draw a straight line because we deal with linear motion. If it's negative, it becomes a straight line. Okay? No curves, no angles, no slopes. Nice straight lines parallel to the time axis. And just quickly, stationary, well, constant velocity, so goes on the y-axis, okay? Goes straight along the x-axis. The shapes are very important. Grade 10s, you're going to get asked to describe motion, okay? Lots for you to take in. We've sort of discussed shapes. I think, Kakleko, we can take a break.
Okay.
I've got a question. We're going to carry on with graphs when we're done, though.
Okay,
after that.
So you guys hear that there is so much more to this physical science show, grade 10s. Come back with all your focus, all your attention, because you really do need this. See you just now.